I hope you guys are enjoying today's meetup. My name is Sida Shen. I'm a StarRocks contributor, and I'm a product manager at Data. So before we actually start, I would like to tell you guys a very, very sad story. Start with a very, very fast sad story. What we do is we build an open source, low latency query engine on top of Apache Iceberg, C++, MPP, right? I really focus on those like data warehouse like workloads. And I do a lot of webinars for our community, right? We talk about our performance. And one day, one of the users just came to me. It's just, I watch your webinar. On benchmark, you're 6 times faster, but it's not, right? I lied. Yeah, and they almost went back to a proprietary system because they were trying to migrate their customer-facing workloads to Apache Iceberg. And after testing us, they just lost hope. They were ready to go back to a proprietary system, which is our own internal storage. But why? It's actually not even an engine problem. It's a small file problem, right? It's it's nothing we can do, right? So yeah, today's talk is about a rant, from the query engine side of this issue, and how we think that we can help with this problem. Okay, so the agenda, we're going to first talk about why keeping your Iceberg table healthy is very important. Right? We're going to talk from a query engine perspective, a low latency query engine perspective, the journey of a query from query planning to a query execution, right, and what this actually affects. And then we're going to talk about how query engine alone, just doing planning and execution is not going to solve this problem by magic, right? And then we're going to talk about our ways of we think we can contribute, to solving this problem. Okay, so let's get started. So why table maintenance matters? So from our point of view, right, a query, from when it's you write the SQL until you get the result, right? Is it go through a network layer, go through a planner, right? And then it gets a physical distributed plan. And our worker knows, go into the storage and scan, what's necessary, right? And then does the query execution. Pretty straightforward, 3 processes. So the planning part, we want the cheapest kind of plan, right? We want the cheapest plan. The difference between a good plan and a bad plan can be 1,000 times difference, right? For query scanning. For data scanning, we want to scan the least amount of data, right? And we also want to do it fast. We want to do it in batches, right? And also for query execution, we want it to be fast and we want it to be scalable, right? So how query engines can help, with the performance. So query planning, cost-based optimization, right? So this is the state-of-the-art, if you want to run multi-table joins, big table join, big table, many table join together, high cardinality aggregations, this is the state-of-the-art. And we want to only scan the data that's necessary. So predicate pushdown and runtime filtering, right? Generates a physical plan and goes to the query scanner. Right? Query scanning is all about scanning fast, so scanning batches, right? So that's why we have columnar storage for Iceberg, and also SIMD, vectorized reader. So basically, for every read, we're not taking it like row by row, at least a few thousand rows at a time, right? And decode using SIMD intrinsics, right? So that way, it's the fastest way of scanning and getting the data. And then query execution, right? So SIMD vectorized operators, make sure that in memory, we process everything by column as well, by batches. The more batch we run, the faster it's gonna go, right? And pipeline execution, make sure, you take advantage of all of the cores you have in the node. And MPP, massively parallel processing, you need to have a way to shuffle the data to all of your nodes, in memory, so it's good for low latency, and also you can run those massive big table join big table and high cardinality aggregations all together, right? And the latency is the summation of all of them. If you mess up one of them, it's not going to work, right? If the query scanning takes like 5.5 years, it doesn't matter like what you do, right? Yeah, so small file absolutely decimates Apache Iceberg performance. First, it blows up metadata, right? Make it even more expensive to read for us, right? And most importantly, is I/O. Right? Many tiny files means a lot of like open and closing for our worker nodes, right? You waste a lot of CPU cycles, right? And vectorization and runtime filter and so all of the crazy stuff we did, it doesn't matter, right? It doesn't matter to the user, if the planning take that long, right? If the scanning take that long, doesn't matter, right? So why is it particularly hard with Apache Iceberg? Actually, the story in the beginning was a little dramatic because that's a problem we see literally every single day, right? When a user POC our system, it's that one Iceberg table that's not managed correctly, it's nothing we can do, right? The first problem we observe is it's always another tool, to fix your data layout, right? In a lot of the teams, the data team that manage the query engine, not the same teams, the team that manage the Iceberg tables. It's not the same teams, the team that manage, the compaction service, right? And also, with the managed solution or internal solutions, internal APIs, right? Sometimes you don't get the parameters you need, to fix the table fast enough, right? And the workloads is different too. Why Apache Iceberg specifically? We hear a lot more from Apache Iceberg than Hive, than other data warehouses, right? Because a lot of our users are moving their latency sensitive workloads to Apache Iceberg, right? And that's where you need table to be healthy, right? And also, a lot of users that are operating those workloads, they're data warehouse users. And data warehouses take care of this automatically. You never think about, small file problem in a data warehouse because it's all solved, right? Given this problem, we started to think, how we can help with this problem, help Apache Iceberg with this kind of problem for like those low latency like workloads. So first, let's introduce, the project we work on, StarRocks. It's a Linux Foundation open source project, query engine for Apache Iceberg, right? Sits on top of Apache Iceberg, directly query it. You get data warehouse-like performance on Apache Iceberg. Simple architecture, no external dependency, just two processes, and supports standard SQL, right? But most importantly, StarRocks is not only your query engine. It actually has its own storage. It's been a data warehouse for years, right? Since its beginning, right? So we know how to do those data warehouse-like workloads. We are able to, with our own internal storage, we can do 10-second data freshness with upsert and deletes without causing query latency issues, right? And for the past 3 years, building the Apache Iceberg integration, what we're doing is basically migrating, porting all of the data warehousing tricks, to the Apache Iceberg world, to the data lakehouse world, right? So make sure that all of our users can have the same kind of experience, the query experience, to run those like low latency, high concurrency kind of workloads without copying their data, with a single source of truth on Apache Iceberg, right? And why don't we do the same, for the ingestion, right? So here comes our attempt, right? So what if we try to solve this problem in the query layer, right? So what we want is query ready for the data files to be query ready immediately after ingest. Bigger files, sorted files, right? And continuous maintenance, on-demand compaction service, a compaction from the query engine, actually tunable, right? So one tool that can take care of most of your writes and maintenance for latency sensitive kind of workload, low latency, high concurrency like workloads. Our effort, so we first introduced our write around half a year ago. More than half a year ago, January 2025, 3.4, and we optimized it, StarRocks 4.0. I just launched it this morning, October 2025. And now I'm going to talk about some of the optimizations that we did and show some benchmark numbers and show our roadmap, how we're going to solve this problem. So basically what we did is write and a compaction API. So for the write, the first thing that we did was partition shuffle, right? One of the problem, of generating small file is when you have a lot of readers, a lot of writers, and each one of the partition has a lot of writers, right? So the worst case, you can have number of files equal to the number of partition and the number of workers timed together, right? So a lot of files. So it's very difficult to get to your target file size, right? So what we did was do a shuffle, right? So make sure that one partition only has one or a few workers working on it, right? So fewer, larger files per commit, right? So bigger files overall to get closer to your target file size, right? And and we did local sorting too within the Parquet file. So sort the pages in the Parquet file, right? So better for query performance. So these are some benchmark numbers between 3.4 and 4.0, StarRocks 3.4 and 4.0. So 3.4 is without the partition shuffle. 4.0 is with the partition shuffle. Right? 3.4 just OOM everything and generating just stupid amount of small files, right? And this file number is actually, it's not even finished because it's OOM. It would have been more if it didn't OOM, right? And 4.0, with the partition shuffle, we're able to generate much less number of files, so much closer to the actual file size target. And then the next is the memory issue, right? So when we write, we buffer everything in memory, right? So without spill, to avoid OOM, we were forced to flush the files early, right? So creating smaller files, right? Then StarRocks has that spill operator, for the query side, which is borrowed it for the Iceberg write. So spill to disk and object storage. So make sure this never happens again, right? So avoid early flushes, so you get near target file size every single time you write. And also, we have a synchronous compaction API. So a synchronous compaction API to fix, your small files on demand. If you see a table you don't like, you just fix it on demand, right? And we have customizable parallelism control knob, so you can use the full power of your warehouse, and you have full control over the resource utilization. So. Okay, so what we're going to do, full Apache Iceberg DDL, DML support in the future, and manage compaction service, because we know how to build a compaction service. We did it for our own internal storage, and also we know the query pattern, right? So we're able to know, we have the information of which table is important, which table to compact first, and also we can give recommendations into how do you optimize your table, create a table, right? And also streaming ingestion pipelines, for those near real-time use cases, right? So, do streaming streaming incremental pre-processing, right? To get your data into Apache Iceberg pre-processed, faster. So here are some StarRocks and Apache Iceberg use cases. PRM Labs is a financial company, blockchain company. Customer-facing analytics, 100 terabytes plus. Customer-facing, low latency directly on top of Apache Iceberg powered by StarRocks. A Red Note, 100 petabyte Iceberg data lake. Better than ClickHouse performance directly on top of Apache Iceberg without moving a single piece of data. And then it's Tencent Game. This is a crazy use case. So they were able to combine our internal storage and Apache Iceberg. So what they did was a petabyte scale Apache Iceberg lakehouse with 10-second data freshness with upserts and deletes. So actual real-time Apache Iceberg lakehouse with a single source truth in it. All of them are Iceberg Summit talks. Please check them out if you're interested. That's all we have. Please join the Slack channel. If you are interested, join the 5,000 folks, like-minded folks, and working on data lakehouses. Thank you. That's all I have. Actually, can I take a picture with you guys? 3, 2, 1. Oh. Thank you. Appreciate that.